Okay, so welcome back. Our third speaker today is Olivier Parcollet. So Olivier is well known for a number of different works, ranging from the calculation of the entropy in the SYK model to developing computational methods for fermionic systems. And he was at CEA Saclay, to which he is still affiliated. And in 2018, he moved to the Center for Computational Quantum Physics in New York, where he leads many activities, in particular everything around embedding methods, and of course the development of the tricks library with Niels Wenzel. So he has focused a lot of his research in the past few years on developing diagrammatic Monte Carlo methods, but in real time, for non-equilibrium problems and transport. And one of the claim to fame is that he has removed the word diagrammatic and the word Monte Carlo from diagrammatic Monte Carlo, as you will see in the talk, I hope.
Yeah,
maybe.
Partly, yeah.
Okay, so the floor is yours.
Thank you very much, Antoine. Thank you for the invitation. It's great to be back here. So indeed, what I will discuss today is the out of equilibrium version of what Michel has been presenting. So we started to try to do out of equilibrium diagrammatic Monte Carlo. And as you will see, we had to evolve the methods and the techniques and to do to more tensor techniques that I will present in this work. So this work is a long collaboration that started about 10 years ago, mainly with my main collaborator. How do you? Yes. My main collaborator, Xavier Vintal from CEA in Grenoble, and a large number of people. I put here some of the references, and including the most recent paper. So the results I will present are, a selection from these different works. So over the time, we moved from, indeed, Monte Carlo technique to more recent techniques, which are more adapted to real time, as I will present in the following. So, why are we interested in out of equilibrium on strong correlations? There are many relevant experiments for that in different contexts, either in condensed matter context with, let's say, pump probe experiments where you excite some system and let it relax, or in mesoscopic physics with systems like quantum dots where you put a small island connected to leads and push it out of equilibrium. These are the systems I will discuss today. But also in out of equilibrium, in ultra-cold atom context with transport calculations. So from a computational physics point of view, the challenge, there is a double challenge. The first one is to develop exact methods, which, as Michel discussed before, we want numerically exact methods that give us, unbiased answer for this system, even out of equilibrium. And specifically for out of equilibrium systems, we want methods that can go to very long time. Let's say after a quench, you quench your system, and then you want to relax to a long time steady state, which is a difficulty for many methods. But however, for the method I'm going to present today, it's not a problem. There are other problems, of course. In particular, we want to be able to resolve various time scales and various energy scales, because in all of these experiments, you have a large variety of time scales. All right, so the system of interest, that several categories, as I mentioned. Today, I will focus the results exclusively on mesoscopic systems and quantum dot model systems for several reasons. First, because they are interest in the physics, but more importantly, because we want to develop high precision methods, and we need systems where we can have benchmarks. And in this system, we have high precision benchmark in equilibrium in particular, because we have better answered solutions. So as you will see, we can compute some quantities with many digits. So we need to be able to benchmark these techniques. Also, you can easily push them out of equilibrium in transport regimes, study their real-time dynamics, and they host the famous Kondo effect, a strong coupling effect, which was predicted a long time ago and observed also a long time ago. So it's an excellent starting point. Our goal, of course, is to move on lattice systems and larger systems, but that's really still work in progress. So I will focus on these kind of systems today. So the idea is extremely similar to what Michel has presented before. we are going to do perturbative expansion. And in our case, of course, we know how to do that. There is a well-established formalism, that's the Schwinger-Keldysh diagrammatic formalism that allows you to do real-time or out-of-equilibrium systems. So if I take, let's say, my quantum dots, just to fix ideas, and I want to compute any physical quantity, could be the charge, could be the current, could be any fluctuation you want to compute, or a Green function, it's a function of 2 times then you have a function of the time and of the interaction u. We are going to consider simply the perturbative expansion in power of u with coefficient that will depend on t. As you will see, we'll be able to compute this expansion, in fact, to larger order because the systems are simpler in real time, up to 25 or maybe 30 orders sometimes. And then the idea is you do this expansion at finite time, at finite number of order perturbation theory, and you extract the physics from it. And the first point I will want to show is a couple of results to convince you that this works. The fact that it works at short time and small u is relatively clear. The fact that it works even in strong coupling regime, I mean in the Kondo effect, it's not obvious. And the fact that it works at long time also is not a priori obvious, and I'll try to convince you that it is the case. So that's the first point I want to discuss. The 2 more technical points, which will be presented in the second part of the presentation, is, well, how do we compute Qn? What are the techniques associated to that? And the techniques are very general. They go well beyond the problem in question here. And how do we sum the series briefly at the end? So the first thing that I can do immediately is start answering this question because, I mean, there is no mystery here. This is textbook. We know how to compute the perturbation series. In this situation, and there's one of the only formula I would really put in the presentation here, we know that in Schwinger-Keldysh you can do perturbative expansion on a double contour with plus and minus contours with vertices at times u, which are, so therefore, with a Keldysh index plus or minus, called alpha here. And there is an explicit formula which you can find in the textbook. You have to do a massive integral in n dimension of some function which you know perfectly, which I will name Qn of t of u, which is basically a determinant of roughly of size 2n, depending a bit on the physical quantity you want to compute, which is formed from the Beer-Green functions. So we know the functions perfectly. The only problem is that we need to compute this integral. So this sums all the Feynman diagrams at order n. It can be done in O2n with Victor theorem. In fact, the calculation is simpler out of equilibrium than the calculation that the CDET calculation that Michel referred to, simply because of this property that the Keldysh formalism remove vacuum diagrams. So you just sum of the Keldysh indices and integrate, and you are done. There is no more complication than that. From inspection on this formula, what we already noted in this paper is that we can see that we are going to be able to do the long time limit relatively easily. And the reason is that if you start and quench your problem at t0, measure it at t, and have your vertices have to be close to the time t if t goes to infinity. Because if it's not the case, you will have some vertices and very far away where the Green function has decayed, and this will cancel with the vacuum diagram cancellation. So it's relatively easy to show mathematically that we can take this limit. So contrary to many other techniques, we'll be able to go to steady state without any problem. Of course, we'll pay a price for that later, and I'll discuss that at the end. So on theory, I mean, we know basically how to do this. The first point I'd like to show is a set of results showing that following this, strategy, I mean, doing this expansion and summing this series, we can indeed find something interesting. So we consider the quantum dot. That I will take a very simple model of the dot, the Anderson model, with 2 leads, left and right, separated by a bias voltage VB, so there are different chemical potential. The leads are, simple non-interacting electrons. The dot is a simple level with a spin and a U interaction on it, no interaction in the leads, and then there is a hopping G between the dot and the leads because of the bias voltage, you have a current flowing through. This is a minimal model for these systems. We know that in such system, correlation effects manifest themselves in different ways. First, as the Coulomb blockade effect, which means that you can have different level of occupation of the dot, especially in the weak coupling to the leads, and famously at low temperature, below the Kondo temperature, by the Kondo effect that opens a channel of conduction through the dot, giving you unitary conductance. In the following, I will use this unit gamma, which is just the width at zero interaction given by Fermi-Golden rule as the unit. So you'll see that in the slide. So what can we do with this technique? Well, what experiments do routinely is to measure the differential conductance through the dot, DIdV, here as a function of the V bias and the gate potential. So I didn't say it, but epsilon D here is the gate level, that's the gate potential for which you can manipulate the occupation of the dot experimentally. And what they observe is this characteristic shape here on the conductance, which is the Coulomb blockade. And here, close to zero voltage, the Kondo resonance, especially here, which is formed, giving you conductivity at low temperature, where a naive, simple mean field model will not give it to you. So that's a manifestation of the Kondo effect. Here you have one electron in the dot, 0 electron, 1 electron, 2 electrons, 3 electrons. So there is different values. The model will, of course, capture only one of them. And the fact is that nowadays, with the methods which I'm discussing, we can actually do exactly that calculation. And you see that we can reproduce what we see in experiments, this different structure here, and the Kondo resonance in the middle. Forget the numbers. I couldn't erase them from the picture. So as a function of the bias voltage and the gate voltage. This is a recent calculation, and the reason is that the computational challenges to actually produce this are, there are a few of them. The first one is to have something relatively fast because you do a calculation per point in this diagram. The second is that, as you have seen before, summing perturbative series can become tricky. Here we have to have a method which is sufficiently robust to be able to do all of this automatically, because we're not going to do each point by hand. And we are going to push this to 20-25 orders in perturbation. And I'll come back to that. In some regime, our integrals are wildly oscillating. So we need, good numerical techniques just to compute it. So we can reproduce this, standard experiments. If I go to a spectral function of the quantum dot, so this time the spectral function on the dot as a function of frequency, here in this point, so close to at the middle of the Kondo resonance, you observe in particular symmetric case here, the famous Kondo resonance pinned here as it should be at this non-interacting value. This is a benchmark because this is equilibrium comparing our techniques to NRG, showing that indeed we can benchmark our technique to numerical techniques which are well established. The width of this resonance here is Tk, that's the Kondo temperature, which we can extract, that the red curve here, Tk, as a function of U. As you can see, we have a nice exponential decay. Again, the black dots are NRG, a numerical renormalization group benchmarks. And you can also see in this figure that if I were doing a naive sum of the series, meaning summing 5, 10, 12 orders naively without doing anything, it will be fine here, but then it will start to explode here at the convergence radius. So you have to do some mathematical trick here to be there. But we can compute that. We can compute the Kondo resonance. We can compute Tk. We also want to plot slightly more than the spectral functions. The self-energy as a function of frequency. Here, in an asymmetric case, you can see the imaginary part of the self-energy as this characteristic form with an omega square here, characteristic of the Fermi liquid, which again is in excellent agreement with the benchmark. So the method actually works, even to very low temperature. You can raise temperature as well. Of course, the interest is to push the methods out of equilibrium. So out of equilibrium, we can now compute this Kondo resonance here, this time as a function of U and frequencies of the color plot. You can see here there is no interaction. This is a Lorentzian peak, which is then giving rise to the Kondo resonance here, it becoming narrower, and which is split here in the presence of a finite voltage due to the non-equilibrium effect. At a finite but low temperature, we can see therefore the Kondo splitting. And the point is that you can do the whole calculation here with one calculation because it's you have the whole series in U, so you can compute the whole function at once. You can compute something which is genuinely non-equilibrium. For example, the distribution function on the quantum dot, which is what would replace the Fermi function in the non-equilibrium case. If you have two leads, you will see that without interaction, that the black curve, you will see two-step Fermi function that are the difference, goes to the two chemical potential of the two leads. If you have an interaction, the curve is modified. It's not an effective Fermi function. There is no effective temperature at 0 temperature. And you have these two functions with a reduced discontinuity here. And you can see we can resum even to very large U, even with a perturbative series. So this is fine. Now I'd like to discuss the second point. At what time did we start? Just how much time do I have?
I guess at 11:10.
Okay, that's just to check. Thank you. So this is, a summary of some results that we can obtain. Now I'd like to come back to my question: how am I going to do this calculation? And the first point is, how do we integrate in large dimensions? We just have to compute, I remind you, an integral in n dimension. The problem is that n is 20, 25, and the function here is in fact widely oscillating in n dimension. So integration problem is well known to be relatively difficult in large dimension. Even if you discretize the function, I will do that in the d number of points. Let's say a Legendre grid or anything, you will have a sum in d dimension. A priori, you face the so-called curse of dimensionality. Your calculation costs you d to the n. Of course, there are ways around that, but the way we want to use it is not Monte Carlo. Here is another way. The fact is that if your functions were separable, I mean, if you could separate variables, then it would be, of course, very easy to integrate. But it's not true. But it's almost true, because your function, in fact, can be represented and approximated in a tensor train or matrix product state. The two words are equivalent here, meaning a product of matrices M1, Mn, M1 depending on the first value x1, Mn on the last value xn, which is pictorially represented usually in this way as boxes for each matrices depending on their external argument, and then you need to multiply the indices in the matrices. And the matrices have a dimension chi by chi, except at the boundaries, because F is a scalar, which chi is being called the rank or the bond dimension, two words for it. So if your function can be represented in this way, and chi is not too big, then the integration, you can just do it on each dimension separately, like this, and then multiply the matrices. So it's like separation of variables. The whole problem is to know where, when is the function like this, and what's the value of chi. A priori, if you can represent any function for very large chi, the question is what the value of chi and what's its dependency in n. So the fact is, the function in question, the sum of Feynman diagrams, is in fact compressible. And that's one we found in this 22 paper, which I quoted before. It's compressible in the time differences, not in the times. That's a small technicality, meaning you can write it as a product of matrices like that. And if we do that, we obtain, let's say, this graph. That's a random slice in 10 dimensions of this function for the charge of the quantum dot, where you compare the exact calculations, I mean, the function, the full expression of the function, and in blue, it's MPS approximation. And you can see it fits the function very well, even with a rank of 30, which is small for tensor network techniques, until we can do several hundred with no big problem. So the message is the sum of Feynman diagram, for a reason we don't really understand, just is compressible. It has a mathematical structure. It's not any function in a low rank structure in matrix product states. Just to insist on for people who are more familiar with tensor network and DMRG technique, this is a quite different use of tensor network that people can be used to. In DMRG, what you do is that you take an ansatz for an unknown function, which is a many-body wave function, and you find this ansatz by minimizing the energy. Here, we know the functions perfectly well. We know how to compute it to machine precision, even though it takes 2 to the n time to compute it. What we want is to compress it in order to integrate it in the compressed form. So it's very different, and in fact, we're going to use very different toolkit and algorithms to do that. They are not based on the same mathematics, so they are tensors, but they are very different to what you're used to if you are familiar with this DMRG or tensor network technique. So the technical question which you want to ask is, given a function, well, can it be compressed like this? And how to compute the decomposition by calling the function a minimum number of times, because if I have to compute the whole function on the grid, I can as well sum it. So there is no point. And of course, can I have an error estimate and know when I need to stop to do this? And so to do that, what we used is a tool which originates in the mathematical communities called the transfer cross interpolation or TCI algorithms, which come from the works of mathematicians, starting with Oseledets in 2010, and the more recent work of Dolgov and Savostyanov. We rewrite it and generalize it in some ways for the physics and presented it in a way which is more easy for physicists in this paper in PRX22. And more recently in a larger paper, which is a large collaboration between us in the Flatiron, the group in Grenoble, in Japan, and in Unique, to summarize the method, develop it, make new variants of the algorithm which are much more stable, and provide examples and 2 implementations in various languages of these algorithms so that you can use it if you want to use it. So I recommend this paper if you want to learn more about the technique. I will not describe it in detail because I don't have time. I just want to say 2 things. First, it's an active learning algorithm, meaning if you have the function, it's a tensor, the algorithm will evaluate some point of the functions. From that, it will build a tensor representation, and then it will decide which new point of the function it wants to evaluate. That's in fact the pivots in high dimensions, and then continue this cycle until you reach some precision or until the algorithm fails. So the summary of the algorithm is that it will compute the decomposition of the function of any function that's representable in this way in a number of calculations which is n, the number of variables, times d, the number of values of each variables, times chi-square, which is much, much less than d to the n, hence the interest of the algorithm. It's a rank-revealing algorithm, meaning it will fail if the function is not compressible. It will reveal the rank, therefore give you a result, give you an information you didn't have when you started. It will provide you an error estimate, epsilon of chi, which will decrease progressively when the rank will increase. Technically, it's basically a generalization in high dimension of Gauss pivoting or LU decomposition. For aficionados of linear algebra, it uses partially rank-revealing LU decompositions in all multiple planes of the n-dimensional tensor. I have some other presentations. I think they are online at the Flatiron, where I give a detailed account of this algorithm for mathematicians. So you can go to that. So application to the dot. Does it work? Well, that's what I showed before. The function is, in fact, a good fit for the MPS. The error decrease 1 over chi to the 4, so it decreases very quickly when you do the learning process. And again, benchmark, we can do it in the beta-ansatz case at a solvable point because you know the solution, so we can do the mathematics, re-expand the solution to 30, 20 orders at machine precision. So you can compute the coefficient. And the relative error of the coefficient, let's say here at order 19, I don't know why my collaborator chose 19, not 20, but is dropping like 1 over chi to the 4th, and we can reach 9 digits at order 20. So with this kind of techniques, and it decreases very, very fast. This method has 2 advantages compared to Monte Carlo. That's why we use it. First, it doesn't have a sign problem, and it's very important for real-time calculations because this function can be horribly oscillating. This is just a bare green function in some cases. It has oscillation, it has a long time scale, a short time scale, and you put that in a determinant of dimension 20, and you want to integrate it. So this method doesn't see the sign problem, besides it's precise. this is an example showing you that even if, depending on some parameters, you can change the sign, the average size of the integral in this problem. Even if the sign drops to 10 to minus 5 here, I mean, the error of factorization for a given bond dimension stays basically flat. Factorizability has nothing to do with the average sign of the functions. They are two different notions. And therefore, you reduce your problem to a 1D oscillating integral. That can be difficult, but which we can handle. So it factorizes the sign problem of very oscillating functions. The second advantage is that because we decompose the full function here, including the time dependent, we compute at once the full time dependence as a function of t for the coefficients, which is great. You can do simple things like changing the start of, the way you quench your system. That's, for example, this example. But even more importantly, it gives us another way to resum the series, which is more recent, and that's the last point which I want to do. How am I doing this time?
You have like 5 minutes.
That's good. That's what I wanted to have. So we can compute the full time dependence in these systems. And the last problem which I need to discuss briefly is series summation. In fact, that's the hardest problem here. Generating the series, we now have better and better techniques, and we can do it. Summing the series can be tricky, and as you have seen also before, in imaginary time. So we also use the same techniques that Michel has described before, conformal map, and we have used that in the early works. It works, changing the starting point of expansion, this alpha shift trick that was mentioned before. I don't want to discuss that. What I want to discuss is something different, which is specific to real time. In real time, you have two properties of the series. First, at finite time t, the series is in fact convergent for all u. One can prove that mathematically. It's a finite volume argument. In steady state, it has a finite radius of convergence. And we can use this fact to our advantage in the following way. The function q of u of t itself also has a low rank decomposition. And that's something we discovered relatively recently, which means that this function can be written as a product of functions with about 3 or 5 functions, about, in some cases, 2 or 3 functions. It's remarkably simple, and it's hidden in the data, if you look for it, which means that if I look as a function of u on t and compute, let's say, the charge here on the quantum dot, by the argument I gave before, at finite t, I know to compute the whole region here well. At small u, I know how to compute because it's weak coupling. So I know these whole regions. Technically, it's below an hyperbola, but it's in these regions. And because the function has low rank, I can extrapolate it to large, long time, and strong coupling. And remarkably, this technique works, not always, but it works for many quantities. Here is a calculation done here in equilibrium again against the beta ansatz. It's perfectly on top. So we can have specific resummation techniques, which again exploit compressibility and low-rank structure of functions, which are specific to real time because of time evolutions. Let me finish by saying that there are many developments that have been started after that using the TCI, revisiting all sorts of expansions in imaginary time in various algorithms which are known by the experts, computing grain functions, using the quantix representation, which I didn't discuss, which is another way of representing function with tensor network, and of course, applying it to more systems. And with that, I will just conclude by saying that this perturbative series, even though they may look naive, when they are associated to proper techniques to compute sufficient orders with sufficient precision, they can deliver results, physical results, even at long time, even in strong coupling regime. And to do that, we discovered from the mathematical community this very interesting technique of representing functions by tensor, which can be used in many cases, and in many cases can replace Monte Carlo. That's insensitive to the sign problem. So that's maybe something that you may want to try in other kind of sums in high dimensions. And on that, I thank you for your attention.